All right. Is it sharing?
Yes, we can see your oh, that's a collab notebook. Interesting.
Yeah.
Okay. Okay.
Yeah. So I'm going to be sharing code I wrote for a directed reading program I did through my school's math department last fall, and we did actually use Colab just because it was easy for us to share data. The project that I focused on was about the thinning of the tear film of the eye, and we're able to measure this using a compound called fluorescein, which has fluorescent properties. And I actually do have a video just because I think it would be easier if it can play for me to show this than to explain it. But you can see that the eye is green because of the fluorescein there. That's the fluorescent compound. And then this area over here where it's getting darker, that's where we're seeing that loss in intensity. And that's how we're able to visually see the thinning of the tear film. So that's where our data comes from, is by measuring intensity like that. All right, so now if I go back to my code, the first thing we did, the first function here is just an ODE. This was used in the paper I read to model the thinning of the tear film mathematically.
Uh,
And then next,
can you explain what ODE are?
oh, it's just an ordinary differential equation. I actually don't know too much about them just because I basically read a few textbook chapters just to do this project. So I haven't actually taken the class yet, but they're ordinary differential equations. And then we used Euler's method. I wrote code to use Euler's method to solve that ODE. And this basically just uses, it's kind of like a linear approximation, and you can use different starting values to solve it. And so this here is my graph of solving that particular ODE using Euler's method. And then let's see, next, I don't think that's not super important. All right, and then so I made these graphs using the equations came from the paper that I read, but basically there's different equations for the height of the tear film or the thickness, the osmolarity, which is basically the solute concentration in the tear film, and then the fluorescein concentration in the tear film, and then the intensity. And the intensity doesn't really end up having units just because it's sort of arbitrary, but it's relative to the intensity over the period of the trial. And then so in this graph, you can see that as the height goes down over here, the intensity also goes down, which is what we saw in the video. It kind of went from green to black. So that's that decrease in intensity. And as that happens, the osmolarity or the solute concentration and the fluorescein concentration both increase because there's the same number of particles, but they have sort of less space to exist in. This is just a different way we did Euler's method. And then in here we have up this section up top. Those are just basically constants. A lot of them are biological constants. So I'm not going to explain those too much. And then we have this function called solve F4. And basically this ends up returning a dimensionalized time space, the thickness of the tear film over time, a dimensionalized thickness, or sorry, a non-dimensionalized thickness, the solute concentration, the fluorescein concentration, and then the intensity over the whole trial. And then so if we scroll down, when we graph those, we get graphs that look like these. So in this first row column, you can see the thickness decreasing over time. And then you have the osmolarity and fluorescein graphs, which look pretty similar, but that shows the increase over time. And then this column on the right is what we're really interested in. That is the intensity graphs. And we're interested in these the most because that's what we use to actually get our data. So we want to be able to get the most intensity that we can. And so if we look at these, if we look at the y-axis, the one that has the highest is this one right here. It goes over 200. And so that's when the fluorescein initial concentration is 1. And so that means the critical fluorescein concentration is 1. So that's what we want to try to use in our trials so we can see the most difference in intensity. And then if I scroll down, I have a similar set of graphs. This just used a different initial thinning rate. And then, so I have another notebook. So in this one, we used a real set of data taken from a trial, and we got it from GitHub actually. So this is just what the raw data looks like. It has 2 columns, which are time and intensity. So the first column just has the time over the trial. And then the second column has the intensity over the trial. So it starts around 91 and then ends up around 53. So the intensity is definitely decreasing. So this is a good set of data to work with. And so we downloaded that as a data frame and then transformed it into an array to work with. And then we had a few different functions that we made. The first one is just the same ODE again. The second one is the intensity function, which calculates the intensity. And then we have this one called solve F4, which is similar to the one in the last notebook. It just has different variable names, but it returns the thickness, the solute concentration, the fluorescein concentration, and then the intensity over the trial. And then I'm going to skip this one for now because it's easier to explain later. And then again, we have here just a lot of variables, a lot of biological constants. So I'm not going to explain those too much. And then this one here, the most important line here is line 4. And this is where we call a minimize function that's built into Python. And we're trying to minimize the objective function that I kind of skipped over before. But it starts with point PT, which is a point. It's just a randomly generated point. And that's basically the first value that it puts in just to get the minimization started. It also has all these arguments, which are the constants that we defined. And then the method that we used was Nelder-Mead, which is basically just, it uses a series of geometric reflections. But I don't know too much besides that because it was just built in. So if we're looking to minimize the objective function, that is this one up here. And what this one does is it calls that solve F4 using for the first time, it uses sort of the V that we've randomly generated, but the next time it'll use that series of reflections to generate the next one. And so it solves for the thickness, concentration, fluorescein, and intensity. And then we use the intensity data to take the Euclidean norm on this line 24 here. So we take the Euclidean norm with the set of data that we started with. So this one here. And then we take that and we square it and divide it by 43, which is the number of samples we had. And then that's the squared divided by 43 is what we actually return. So that's what we're trying to minimize. So it's sort of like a least squares regression. We're trying to minimize that. And then so if we go down here, that's what we minimized here, and that's what we get as a result. But what we're actually interested in is the V0, the initial thinning rate we put in to get that result, because that's going to be the one that best fits our data. So that's our solution here, which is X. And then so we ran that. We can see there's a few things down here. We have that the optimization terminated successfully. So basically that it completed. And then we also have this NFEV, which is 30. So that's basically how many reflections it took to get that minimum value. And then the answer we got here, our XR solution is 0.43. So then once we have that, we basically just have to redimensionalize our solution. So we multiply by D, which is the starting height, and we multiply that by 60 and divide by TS, which was, I think, basically, we got that when we non-dimensionalized our time. So once we redimensionalize that, we get that the thinning rate is about 7.7, and that's the one that makes the ODE best fit our data. And so we're able to graph that. The line here is our prediction using the V0 that we generated, and then the scatter plot is the actual data that we had plotted. So it's a pretty good fit. And then using that, we're able to just then calculate the predicted height, osmolarity, and fluorescein concentration over that trial as well. That's all I have.
Thank you. Okay, who want to go next? Abdul? Okay.
Okay, so basically, this is a tic-tac-toe game using classes in Python. So to make this game, I used about three classes, one for the board, then one for the player, and then one for the game. So, so in the board class, I created an array of empty elements which would represent the um the spaces where players can enter characters. And then I also created a function for printing the board every time a player enters their position. And I also created a function for updating the board when a player enters their position to play in. Then I created a function to check the winner of the game. So basically when like three when three rows or three columns are filled with the same type, then the player wins the game. And then I also created a function in the board class to check if the game ends up as a draw. And then in the player class, I used the constructor to initialize the type of the player. So you can have two types, player X or player O. And then I created a function to get the name of the player. And then in the game class where everything happens, so I created a constructor to initialize all the characteristics like the player one, player two, the board, and the current player. So I called all the other classes inside this class. And then I created a function called play. This is where everything happens. So this is an exception where um you, you ask the player enter the position you wish to play in, and then the player enters their position, and then updates the updates board from the board class is called. So the position is updated, and then I call the print board function, and then the board prints after. And then after that, I check if if the game has ended by checking the check winner function, and then if it's true, then it prints congratulations, you win the game. Then if not, then the game is a draw, and then I switch the player. So is a is a variable called self.current player. So this switches on every turn. So first it's player one, and then it switches to player two because of this condition. And then I also used exceptions to make sure that if a player enters an invalid position, like it doesn't bring an error, so it just prints invalid position entered. And also did something in the board class to check if the position has already been selected, and if it has already been selected, it prints invalid arguments enter no, it prints position has already been selected. So if I run the game, so I call the game class, and then I call the play function. And then if I run the game, uh, yeah, yeah, bro. What the hell? So it's a game that's played between two players. So I enter the position I wish to play in, and then it updates the position on the board. Then it's 3, 6, 7, 9. Which way? So select 4. And then like 5. And then I win the game. So yeah. So
Oh, thank you. Want to go next, Emma or one of the Jones brother? You mean when you say we, do you have a one presentation or you have separate? Okay, that's fine. Yeah.
So this is our project, Tropical Treasure Hunt. Wait, can I move this screen out of the way? Okay, awesome. So this is Tropical Treasure Hunt. This is a hackathon project we had worked on. It was early this year, around February. It was hosted by Auburn Hacks at Auburn University in Alabama. And we decided to do a VR experience. And it was a team of 4 people. So it consisted of myself, my twin brother, my twin sister, and then our friend from class, Sierra.
Wait, you have a twin sister as well?
Oh, Kaya.
Okay.
Yeah. But yeah, which is us 4. And what we did, it was the theme was tropics, like underwater, or really it was how you interpret it. It could be like an island or underwater, but we did an underwater adventure game. To preface the hackathon, we went to it annually changed their theme for what the coding challenge would be based around, and this year was tropical themed. So after we basically figured that out, we then wanted to make a game revolving around that theme to better fit the overall vibe we wanted for our project to have. And the coding language we used was CodeBlocks. It's a block-based programming language that's actually pretty akin to the language Scratch, if you ever heard of that. It's kind of an older language. So we decided to use this language because our sister was already familiar with it because she used it to make programs on the Oculus headset. So a couple of the challenges I ran into, I don't know, usually when you play a video game, you don't really think about this, but there's a lot you have to go to when dealing with user input. So we, like, before anyone even got to play it, we kind of had to, I guess, determine what the user was going to do. And like, if they went out of bounds, we'd have to have like a warning, then just a bunch of stuff for, I guess, this type of game. And then this is a decision-based game, and it has different outcomes depending on what decisions you make. So we had to equate for a bunch of that. And then we would ran into a lot of glitches when it came to the player choices with like our functions and then our conditionals. But we got past it. And some of the accomplishments we were proud of is that we were able to do this. And I guess technically they gave us 24 hours to work on it, but it was actually less than 24 hours because during the hackathon, we had a bunch of events that we would go to. We met a bunch of companies and just played a lot of games. But yeah. And then here's a look at some of the my GitHub repository, some of the CodeBlocks that we had used, our function, and the turtle, his name was Turt, and he was like your guide during the game. And just some of the things that would like make him run depending on the user input. I'll go back to the top one. Yeah. I believe that this code made our NPC Turt like move around. And we also implemented our own audio to make him speak. Yeah, and we like recorded our own voices and stuff for some of the other characters. Mm-hmm. And it would match when he would turn clockwise or counterclockwise, so that anytime that the user clicked on the NPC, the audio would match when anytime he was moving. So. And yes, essentially it.
So this is a virtual reality. So you put the
Oculus Quest headset.
Yeah. Okay.
If we had it with us, I mean, it would be a really cool demonstration. Yeah, we left it back in Nashville. Yeah, it had its own ID that we could like use.
Yes. Oculus. Interesting. Okay, so Emma. Ready?
Okay, so my background is mostly in climate science and physics, not necessarily computational science. So I thought it'd be cool if I showed you guys some this physics lab report that I wrote up. And then also yesterday night, I learned a little bit of Python, so I made this like simple game. But yeah, so basically, this is like a paper that verifies. So what I studied was how does distance impact sound intensity? And it's already been proven that there's this like specific formula, which I mentioned somewhere down here. But it's basically just conducting your own experience to verify that. And so what I did was I designed my own kind of experimental procedure where we have this measuring stick over here, and then I step back by increments of, I think, 1 meter. And then I used this software here to measure the sound decibels of my flute. So I'd play from 1 meter, 2 meters, and then I'd kind of step back to measure that with my computer. Or sorry, it's 1.5 meters and by increments of 0.5. But yeah, basically, I got data from Vernier, and then what I did was I took so I did a bunch of math here. It's kind of boring. But basically I ended up taking the data and plotting it on this graph, and then used logs to apply a curve fit. And I think a lot of what this is just determining uncertainty. And a lot of stuff actually went wrong with this experiment. I found out that there was just so much uncertainty, and part of it was because the Vernier system that I was using was broken in some ways, and it was just wasn't very accurate at measuring sound intensity. But ultimately, I did find that there was a correlation between distance and sound intensity. It just didn't exactly match up with what was supposed to happen, but it was still kind of cool though to kind of do my own experiment with that. But yeah, all of this is like measuring uncertainty and stuff like that. But yeah.
So this is your lab report for physics?
Mhm.
Oh, interesting. But do you get the sensors? Do they provide the sensors for you?
Yeah, we're using Vernier lab sensors, and that
I
was what
see.
I was talking about with the errors. They gave us
Okay.
these sensors, but they didn't work super well, so that's why
I
we
see,
didn't
I
get
see.
the results that we wanted. But
Oh, Vernier, those classroom.
Yeah.
I see.
Yeah.
Okay, I see. Okay.
But yeah, I also have this like little game that I made. 1 second. I think I need to like reshare it. Yeah, so yesterday was my first day kind of working with Python, so I don't know a ton yet, just because I don't have like a computational science background. But I did work a little bit on this game. So like if you've ever seen those kind of like scammy Magic 8-Ball games in the store, basically like you just kind of shake it up and it gives you this random result, and you have to ask the Magic 8-Ball yes or no question, and I kind of made that all here. And then I guess like the one fancier thing that I did do was I made it so that you could play this game in both English and German. So what you start off with is it starts by asking you your name, and then after you insert your name, you just type whatever question and the yes or no question that you want asked. And so it runs the system that randomly generates a number between 1 through 9, and then these are the associated answers with that. And so and then this right here is just if you want to continue or break. And so if I run this, wait, can you guys see the other screen that pops up?
Yeah. You only show that this is the screen where.
Oh, there's like another one when I run it. Hold on.
You need to share the other one.
Yeah. I'll just share my desktop.
Oh, I see. Now we see that the ID shell screen.
Yeah, and then so, oh, sorry, you
Can
have
you
to
put
type
German?
for language
Not that
first.
I understand German. I just want to see how it works.
Yeah,
Anyone
so
here understand German? Okay,
yeah, so this just asks what is your name,
I see.
and then what's your question? So like,
I see.
so I
Okay.
win the lottery, and then it says absolutely. And then this is yes or no if you want to continue.
Oh,
Yeah. So that's it.
interesting.
Super simple, but
okay.
yeah.
Wow, this is interesting. So we are learning Python and German at the same time. Multitasking. Okay. I think who anyone online who online want to still there.
Yeah. If everyone finished,
Tyler,
I can go.
Cameron,
Dr. Shen,
me,
am I audible?
Louis, that's just Jane also.
Am I audible?
VG, I mean, you want to share something or just talk
Yeah,
about something about your own project?
sure. Am I
Uh-huh.
audible? Am I audible?
Okay.
Am I audible?
Oh, yeah. My speaker is off there. Thank you.
Okay. I can. This is my research project, my thesis project. So my project is for focusing on optimizing the traffic signal traffic signal timing. So our goal is to use the reinforcement learning in machine learning concept and optimize the traffic signal timing. So we have chosen the MLK Boulevard, 11 intersections, the corridor in Chattanooga, and we are using those intersections for studying the data and develop the model and optimize the traffic signal. So this is our model. Actually, in this project, multiple college teams are involved, and my area is for developing this model to optimize the signal timing. So our model uses the graph neural network with reinforcement learning. So we first we take the model of the road network and build into the graph format, and then tie that each intersection to a individual node. That individual node we call it as a reinforcement learning agent. So for each intersection will be tied to each oral agent, and they will observe the local first they'll observe the local traffic information, and that is called a state, and feed it to the model, and model will learn from the state and predict what would be the next possible action is like for stay in a current signal state in green or switch to the other phase, that is the action. So a model will tell the most appropriate action and will apply the action to the intersection traffic controller, and again observe the state and see how was the performance. So to measure the performance, we are using the icompbio, which is calculated based on the number of stops and stop delay at the intersections of all the vehicles. That is brief overview of the model. And in the initial testing, like we observed out of 11 intersections, we observed like almost like 7 intersections have performed in performance have improved, and overall we see around 18.86% when we tested with PM peak hour during that first hour simulation. And in the whole PM peak hour, the 3-hour simulation, we observed around overall 15% to 16% improvement. And in 24 hours test, we observed around 28.505% improvement. We are continuing to fine tune the model. In this, from the yesterday session, what I was able to use it like here in my code, like for going through each intersection, I'm using a for loop, and I wanted to implement the threading in the parallel processing so that model will perform faster. The execution will be faster. But the challenging part is here, my model interacts with the simulator, which is a VISIM, PTV VISIM simulator, traffic simulator. So that is a EXE object. So like when I was using in threading, it was not able to like access the shared object. That was the challenging I had. So after yesterday's class, I was able to use the ChatGPT. So I asked how to implement the. I just simply asked first Python multi-threading. Then it gave me simple threading code. Then further, I asked the question multi-threading with shared exe. Then it gave me the COM object with the shared exe. But with this method, I know it will not work. It will not share the object properly especially with the VISIM model, because I already faced that issue. So then I reframed my questions. There is a Marshall objects in Python which we can use co-initialize the Marshall objects. So I asked a question directly how to marshal the exe object. Then it gave me the options how to do. Simply marshal the object. Then I asked how to use the marshaled object in multi-threading. Then ChatGPT gave me option like how to use and marshalling the object with multi-threading. But that was again, it gave me the simple with the simple threading, but co-marshalling is the one we have to specifically use. Then I put that question specifically how to use what is the best option, whether co-marshal or simple com type. Then it gave me the explanation of it, and I asked an example with co-marshalling interface and multi-threading. Then it gave me another version of example, and this worked, but this had an issue again while sharing the object. So I put the error because there are objects in Python co-initialize EX. It's not able to identify the object. I gave again it gave me different version of code, but with a single thread it gave. Then I asked how if I want to use 11 thread or more. Then it gave me how to initialize multiple threads with the co-marshaled object. Then it was throwing an error when I used that code. Then I gave that error. The above code throws this error. Then it came to the point that sharing is not happening properly with the last version. So then ChatGPT gave me the updated version of how to share it. Actually, that code works fine. The last updated version, it works fine. Now with I tested that code also with my code version. My last run, you can see like it ran without error. And my output, I even just generated this output were just generated today. So through that updated code, so it works fine. But I felt it is little bit slow. So I asked why it is slow, because we are using the thread logging, the parallel processing when the object the simulator is locked in a thread. So it's wait for another thread is waiting for it to complete the execution. That's where the slow. So it gave me another version of without locking the thread, but I yet to try this. And this one is a little bit risky. I want to make sure it works fine and test well. So it gave me. So what I came to say is like yesterday from learning that it's like a ChatGPT is like interactive way of searching for content. So when I rephrase my questions and based on the previous responses, and it's able to adapt and give me the responses at what I wanted. So that's really helping. That's about my thing, my project work.
Interesting. You use ChatGPT to help you optimize the multi-thread coding.
Especially I used for multi-threading. My model was running very slow actually. I'm improving. Like initially it was working. One of the I have two versions. One is just to observe the actuated. So if you see actuated took 2 hours 34 minutes. After implementing multi-thread, I was able to reduce 1 hour to run in 1 hour 25 minutes. But still, I want to reduce it further. That's where I want to share this. Actually, this is the PTV Vism traffic simulator, and this object will run through COM, and this should be shared. So when it's shared, I need to read the current state of the object. So then that's where the problem I was going through the last week. So now ChatGPT helped me for that.
Okay. So those are the is that the MLK corridor?
Yes, this is MLK corridor.
I see. I see. So where is that Miller Park?
This is from actually Pine Street, from Pine Street to Central.
Well,
Pine Street to it passes through our sim center.
oh, that green, is that the green place, the Miller Park in the middle?
Maybe, yeah. This one might be. It
Yeah,
might
that
be.
looks like Miller Park. Yeah. So
Okay. Yeah. So
Yeah.
this is our area for now.
okay. Okay. Thank you. That's yeah. Thanks for sharing this.
Thank you. Thanks for this opportunity.
I mean, do you want to talk something about your project, your research, or whatever you are working on?
Sure. Recently, I did a project in the fluid mechanic. I would like to share this presentation.
I mean, if you're, oh yeah, we see your sharing screen. Oh, gee, a lot of math formula here. Okay, that's fine. Yeah. Go ahead. Yeah, very good learning experience for everyone here. So,
Okay, in this project, we should solve this system of nonlinear PDE system of equations for simulate the behavior of the fluid in our domain. We have.
can you explain what is LES?
LES is we can in numerical model we can simulate the behavior of the fluid by DNS, direct numerical simulation. That is very expensive and it's take ages to get good answer for by using this method. On the other hand, we can use the LES model that we can get an answer quickly and more accurate compared to, for example, to a RANS model. This is a model that simulates the behavior of the fluid.
I see.
Okay. In this model, we filter the governing equation, then we obtain this equation. We have mass, momentum, chemical species, and enthalpy equations. In this project, by machine learning, I predict this function. For this project,
hey, I mean, can you go back to the previous slide?
Sure.
Can you explain why you are using those formulas? Like, for example, mass, I see partial derivative equals 0. But then what do they mean?
Okay, this is by writing the governing equation for mass particle in our domain, we can obtain this formula. You can, for example, if we have an incompressible flow, that it finally we could we can ignore this term, and we have for example this equation, that it means in each direction we have the input equal to output.
So conservation of mass.
Yes, exactly.
How about the second one?
This is after writing the, for example, the force equations for or control volume, we obtain this formula, these equations, which can say the if the total force that we use for or control volume is equal to the mass times 2 acceleration. For example, this is a pressure. This is a force that we obtain from the this term we obtain from the diffusivity of the momentum. This is a term for a convection of momentum. And in the other equation, we have a equation for chemical species in for each component of our fluid. The final equation is the energy balance of our the conservation of energy, which means that, for example, the input minus output could increase the energy, the internal energy of our control volume. This is the equation that we can obtain from the conservation of mass. This is the equation we can obtain from the conservation of momentum or forces. This is for chemical species that finally that for conservation of energy.
Okay, thank you. So we have a mass, momentum, chemical species, and energy.
Energy. In fluid mechanics, we should solve based on our problem. We should solve these equations simultaneously.
I see. Thank you.
You're welcome. In this case, I use the DNS case for to create exact value. I use, for example, 224 CPU core for this for each cases that took for example 48 hours. Then by filtering the domain, we can I can extract the proper feature that finally I create 125 million samples, then feed these samples to or training or artificial neural network model. Then I convert the terrain model to a Fortran 90 to a speed up parallel processing for CFD simulation, but I cannot show this Fortran code because this code belong to Georgia Tech and DOD. And I'm not able to show you this Fortran code. And finally, I run the CFD code by trained Fortran module. And in this slide, you can see the impact of features in priority test. At the first step, I use the velocity in the X, Y, and Z direction for training or model. you can see the loss and percentage error here. But in second step, I increase the number of feature. For example, I use the strain rate tensor and rotation rate tensor and RE-top, that is the which means the frictional force on the wall, if we want to translate it. And then by adding these features, you can see I drop the loss and percentage error 10 times. After this section, I convert the code to the Fortran F19 and then run the CFD code again, and this is our result. For example, this is a DNS or exact result. This is the LDKM model that is very famous model the scientists used in LES model. And this is our result by hook it up the train model in the CFD code. And here we can see the surface tension contour for smooth wall. In this case, we train the model for smooth and rough wall. As you can see, the DNS case is here, the exact result, and LDKM is this one. And finally, we have the ANN model. As you can see in entrance and the output of the domain, we have some problem, but we resolve this problem because in this case, you can see we need extra features for training or model. For example, in this case, we should import, for example, the location of each element to increase the accuracy of our model. But in a rough case, as you can see, we have a similar result compared to DNS model. This is the result for surface tension contour for DNS, LDKM, and this is for ANN model. And in this slide, you can see the turbulence intensity in the for both smooth and rough cases. As you can see, in smooth cases, we have a higher turbulence intensity in our ANN model, but in rough case, we obtained a good result for train the subgrid scale model by the ANN algorithm. Thank you.
Thank you. That's quite a lot. I'm impressed. Okay. Okay. I mean, I guess I'm confused. You are doing computational fluid simulation. Why do you have to apply a neural network here? I missed. I'm just missed. What are you trying to do here?
Okay, there are some traditional equations that the scientific use for model or predict this term. The whole problem into solving this equation is finding a prediction model for this term. And in this case, I train our model to force the model to use the trained ANN model compared to, for example, the LDKM model. Just a moment. I published this in AIAA. Journal. Okay, here. For example, the scientists used this equation for solving this problem, but finally they couldn't get a good answer because they don't consider the proper features for predicting this function. And in this case, we increase the accuracy of the LES by adding the by using the predicted model by ANN.
Yeah, this is part I'm really confused. I mean, you are doing simulation, but then somehow you use the machine learning, and then you say the accuracy predict. This is part. What is your neural network model trying to predict? I guess I'm missing that part.
Okay. In this case, I trained this model. At first I generate the labels by running the DNS cases, right? And after that, I use the DNS data and then filter by using the filtering the data, the volume average filtering data. I create the LES data from the DNS data. Then I use the DNS data for training or for training this equation. And after that, I import, for example, velocity in UV in X, Y, W direction, and they obtain the tau ij SGS, which means this term. And but after this step, we have a function that we can import the U and get the tau ij, the correct answer.
Can you explain what is the tau you are predicting here?
Here, this is our.
I see. That's moment. Some measurement of momentum.
Yes, exactly. As the whole problem in this case is finding, because we have this in solving this equation of system. We at the previous step we have this U tilde and UJ UI and UJ tilde, but we don't have this term. We should predict this term. There are many solutions for this term, but all of them are not very accurate. In this case, we use the machine learning and train this model, then train this equation, and then use train model to solve this system of equation by the train model.
Okay, but okay. My apology. I probably asked questions.
No.
So my understanding about the governing equation is those, because those can be solved by numerical simulation. If the system is there, that means the second part momentum, it should be solvable all by the traditional method. I guess
this equation.
Yeah.
How we can solve this problem, because from the previous step we have the UI tilde and UJ tilde, and we have the pressure.
Okay.
But we don't any information about this parameter.
What is that? What's the difference between I and J? That's the.
This is a tensor notation. I is from 1 to 3 from the X, Y, and Z direction. For example, U1 is the velocity in X direction, U2 in Y direction, U3 is the velocity in Z direction.
I see. That's
okay. This is a tensor.
That's a tensor.
Yes.
Actually. Okay, thank you. I really appreciate your patience to explain all this.
Thank you too.
Thank you. Okay.
Thank you so much.
I appreciate everyone trying to explain their thing to me, everyone else. So I don't know about you. If I don't keep doing the same thing again twice, I get bored. So in a way, I'm not fit to do a work in a company or something. I would just I cannot sit there or to do the same thing again. That's yeah. Anyhow, that's just me, but I'm sure I don't feel. Okay. I think we can call it the good ending. So, oh, by the way, actually, before you leave, I need you to take another survey. Hold on. There's actually we should do that before the morning session. So there's a post survey just to gauge you a view on the generative AI. So let me post that in the chat window. So if you can take that survey, it would be really helpful to us. So I'm going to put that in the chat window.